Mama, your phone will work for fast.
It's up when she. Mo ti ọlọ́pàá dé mo rí ọmọ ṣe.
Good morning, everyone.
Good morning, sir.
Okay, how are you?
Good morning, sir.
I'm fine, sir.
Okay.
Fine, sir.
Now the live streaming is on now, so I want perfect decorum, everyone. It's only when I ask you to ask questions, please, that is when I want you to talk. So the live streaming is on so that you don't disturb those that are making use of the YouTube channel. So I want perfect decorum with the class, and so I will share my slide now and commence the class.
Yes, sir. It's better.
So for today's class, we will be commencing the class with linear momentum. And with that, we will I share the okay. So today's class, we will commence with linear momentum. And these are part of what we've been taught from our O levels. And it is expected that we understand a bit of it, and we will go over it and solve some problems. So, however, we will
I don't work like that. I work like a soldier.
Okay. Please, I have informed you that I want perfect silence, please. I want perfect silence, please.
Yes, sir.
So now, today's class will commence with linear momentum, which now leads us to center of mass. We will describe center of mass, and we will actually understand what that implies. So when you say something is linear, linear means it's moving in one dimension, either across just the x-axis alone, or just along the y-axis, or just along the z-axis. So whichever of the axis, but it's only going to move, you can only describe that kind of motion along just one axis. So that is what we refer to as linear. And when you talk about momentum, we all have a situation whereby we have objects moving, even around us. We see people play football, we see cars moving, we see so many things moving around us. So when they move in that manner, it is observed that they actually have some form of momentum by which they move. And if you actually look at what I have here, we have some balls here now, and you found that the ball is moving. For those of you putting down your name, you don't need to do that. You are disturbing the class, please. For you to come in, you would have done some registration. So that's enough for me. The attendance has been taken. And for those that are online on YouTube, everything is perfected and well taken. So now you find this ball actually moving from this point A now, you find the ball moving in this direction. You find it moving in this direction. However, by the time it gets here, this is ball B. It's colliding with ball B. And after the collision, you find out that they move in separate ways. They move in separate ways. Ball B was initially at, that's our U2, was at rest. While the U1 from year 2 is moving at a specific speed. So that is the observation. So by the time it gets here, it collides with the stationary body and they move in separate ways. Now, what you have here now, this is the ball moving after collision and the other ball moving after collision. So when this happens, linear momentum is usually given as a product of the mass of the body and the velocity. And that is why you have the M and the V's. Is a product of mass of the body moving and its velocity at which it is actually moving. The velocity at which it is moving. And that is what we have there. Now, what we'll be discussing today, we'll discuss about momentum and its relation to force. We'll also discuss about the conservation of momentum. Likewise, we'll discuss about collisions and impulse. Thereafter, we'll also discuss about conservation of energy and momentum in collisions. Also, we'll discuss about elastic collision in one dimension as well. Also, we also discuss about inelastic collision. Thereafter, we discuss about collisions in 2 dimensions and 3. Then we discuss about center of mass for human body, and center of mass and what is referred to as translational motion. Now, momentum. How is it related to force? For every object to move, a force must have been exerted on the object. And that is what is going to take us back to the Newton's second law, which says that the F is proportional to A. So when you then introduce the mass, which is the constant of proportionality, you have this. So a force must be exerted on a body for it to move. So momentum is a vector symbolized by the symbol P. This is just a symbolical representation. You can use T, you can use whatever you like. In some tests, you can find momentum represented as something else, in as much as you know what it represents. So you can define it as a product of mass and what? And the velocity. So from what we have here now, the rate of change of momentum is equal to the net force. Rate of change of momentum is equal to the net force that is applied. You have an object moving, let's assume a ball. A footballer kicks a ball on the field. The ball gathers momentum and it starts to move in the positive X direction. Now, as the ball is moving as a result of the force provided by the football player, the momentum is also changing because the speed is also changing with distance. So because of the change in the speed, because the mass of the ball cannot change from here, what we change here is the speed of the ball or the object. So as the speed changes, the momentum also changes. So because the speed changes, momentum as well changes with respect to that, with respect to the velocity, because it is directly proportional. So because it is changing, because of the changing nature of the velocity, we can then discuss about what we refer to as the change in momentum. So the change in momentum with respect to time gives us what? It gives us the net force that is applied. It gives us the net force that is applied. It gives us the net force that is applied. So the rate of change of momentum, that's why you have the change in P with respect to change in T. So, and that is always equal to the net force that is applied to the object. Now, from here, we can then say from here, if the summation of our F, so change in momentum would then be equal to M, V minus U divided by what? Divided by T. Because this is rate of change of momentum. Momentum changing with respect to time. So if you cross multiply, here you have F multiplied by T, which will give you the change in momentum. So we see later. What we have here is referred to as impulse. Impulse is equal to change in momentum. So we'll see that in subsequent slides. So from here, we can then move on. We all know that under the conservation of vector quantities, one of such things that are conserved are energy, momentum, force, and so on and so forth. When it's lost in one situation, it is gained in the other situation. So we then can conclude that it is neither destroyed nor created. So during the collision of objects, measurements have shown that the total momentum does not change. Total momentum does not change. And that's why we have momentum of the object before collision will be equal to the momentum of the object after collision. Before collision, the total momentum is equal to total momentum after collision. Now we have two bodies, body A and body B, moving in opposite direction. They are moving in opposite direction and they therefore collide after a while. And this is the collision of balls A and B. So when they collide now, they move separate ways. But however, in the process of the collision, momentum is what is conserved. So it then implies that energy lost by one is equal to the energy gained by the other object. Energy lost by one object is equal to energy gained by that object. And that is what we have here. Then moving as well, we have a situation where you have coaches of train, coach A, and you have coach B. Coach A moves with 24 meters per second, while coach B is at rest. When coach A approaches coach B, it collides with coach B. So here we're asked to calculate the final velocity. After collision, you can see the two of them got stuck together and they move together. If after collision, they get stuck and they move together, this is what we refer to as inelastic collision. This is what we refer to as inelastic collision. That is what we refer to as inelastic collision. They collide, they get stuck together, and they move with a common velocity. But if you look at this situation now, they collide, they move separately with different what? Velocity. This is what is referred to as what? Elastic collision. This is what we refer to as elastic collision, when they collide and they move their separate ways. Elastic. But when they collide and they get stuck together and move with a common velocity, we refer to this as inelastic collision. So any question? If you have questions, unmute yourself to ask in 1 minute. Okay. I'm with you.
Sir, I think we've had this class before.
I know. I am moving towards center of mass.
Yes, sir.
So,
Sir,
yes.
after the collision, during the inelastic collision, sir.
Yes.
After the collision, what will be the new velocity of the object?
The new velocity of the object will be determined from your law of conservation of momentum from here. So all you just need to do with this kind of situation is just for you, if you give this MA, just like it's stated here, MA, let's say the initial velocity is UA plus MB, UB will be equal to MA, VA, which is the final velocity plus this, MB,
Okay,
VB.
sir.
But here they will have a common velocity, which will just be V. The masses will be together because they are now stuck together. And
Okay.
you insert the appropriate whatever here and make V the subject of the formula. So you can always calculate the common velocity.
Okay, thank you, sir.
Okay. So from here, when you have a rocket at rest, now the rocket is propelled. So you can see the gas that is released when propelled has some momentum that is in the opposite direction to the direction of the rocket. So that's what you have there. So momentum is always conserved. Now you have impulse here. Just like I stated earlier, if you have that the summation of the forces is equal to the change in momentum divided by T. The product of the force and T will be equal to mv minus u. So it then implies that your impulse is the same thing as your change in momentum. Now, what is impulse? That is what is very key. When you discuss about impulse and you are asked to define impulse, do we have some wrong notion from the secondary school? And usually you see students miss this question during WAEC, moderation and grading of script. Impulse is a product of a large force acting within a very short time. Like you see this long tennis ball now being hit by the lawn tennis player. You will observe that it's a very large force that is applied, or a carpenter driving nail into the wood. If you have a carpenter driving nail into the wood, what you have is that he strikes the hammer on the nail with a very large force. But the duration of interaction between the hammerhead and the nail is very short. It's very short. So when you're asked to describe impulse or define, it's not product of force and time. It's product of large force and short what? Short time. That is what is referred to as impulse. So these are just some diagrammatical representation of impulse. You see the time is short and the force is large, acting within a short time. Now, we discuss about collisions and impulse. The impulse tells us that we can get the same change in momentum with a large force acting within a short time. Can you see that? Or a small force acting in a longer time, vice versa. So this is why you should bend your knees when you land. When you land, you bend your, for example, if you are jumping from maybe from the fence of a house, you want to jump over the fence down. When you are landing, make sure you bend your knees to minimize the impact on your kneecaps. So these are some of the things that are necessary. And while landing on a pillow, other than landing on a concrete. So you need to bend your knee. These are some of the techniques. Now, momentum and collision, you can see this. This is what we refer to as a inelastic collision. They get stuck together. And this is an elastic collision. They move their separate ways. Now, so elastic collision in one dimension, which means along the x-axis. Now, we have a situation with an inelastic collision. Some of the initial kinetic energy is lost to thermal and potential energy. It may also be gained during explosion, as there are addition of chemical and nuclear energy. So a completely inelastic collision is one where the objects stick together afterwards. So there's only one final velocity, like we've mentioned there earlier. So in 3 dimensions, with the collide, you now want to describe the collision in terms of the X, Y, and Z. So that's what you have. So these are some of the basics of solving problems under collision. Now, we then move on to center of mass. What do we refer to as center of mass? In A, the diverse motion. If you look at the diagram we have there, you will observe that you have a diver. This is one diver. 2 of them exhibiting different motions. You can see from the board, this decides to jump into the swimming pool in this manner, moving in this manner, in a projectile form. Also, the second person in a projectile form tries to roll himself or herself while trying to dive into the swimming pool. Now, the diver's motion is pure translation. This is pure translation. Moving from one point to the other, the position is not changing. While for the second one, it is translation plus what? Plus rotation. This second one is translation plus rotation. So there is one point that moves in the same path a particle would take if subjected to the same force as the diver. So this point is called the center of mass. So there's a specific point that moves in the same path, that is on this body, the body of the human being. There's a specific point that takes the same path when it is subjected to the same force as the diver is. So from here, this is another similitude. General motion of an object can be considered as the sum of translation motion of the center of mass plus rotation plus vibrational or other forms of motion about the center of mass. So usually motions are performed about the center of mass. Motions are usually performed about the center of mass of some group of atoms or objects. Now, how do we calculate the center of mass? The center of mass is also closer to gravitational center. Gravitational center is the point at which the Earth's gravity acts on an object, while the center of mass is a path through which an object takes. It's a path. But this is like a force acting at the center. This is the earth pull, the earth's gravitational effect on an object. So for two particles A and B, the center of mass lies closer to the one with the most mass. You have particles A and you have particles B. So the center of mass in this case will lie closer to the one with the most mass. That means the heavier one. That's where the center of mass will tilt towards. That's where it will tilt towards. So now from here, if you sum up both masses, gives you a capital M. Why this remain? So the center of mass you have here, you can see is inversely proportional to the total mass of the object we are considering. Why this center of mass you have here is directly proportional to the summation of their linear momentum. So the center of mass lies closer to the one with the most mass. So it's just like having a mass of 40, you have one that is 60. So if you are summing them up here, 40 plus 60, you can see that's 50. So the 50 center of mass you have been able to get is closer to which one? It's closer to the 60. So that is what that is describing. Any question?
Yes, sir.
Any question?
So you said 40 plus 60.
No, sir.
So I said 40 if you have two masses, because the statement says that the center of mass lies closer to one with the most mass. For example, now if you have a seesaw, you are sitting here, your junior brother is here, he's 40 kg, you are 60. The center of mass of this plane seesaw will be closer to where? Be closer to the one with the largest, the larger mass. So 60 plus 40, that's 100. If you find the average, what do you have? That's 50. So it's closer to the larger one.
Okay, sir.
So that was what I explained. So from here now, the center of gravity is the point where the gravitational force can be considered. So we can see a difference between center of gravity and center of mass. So since center of mass is the point at which the constituent of the object, what makes up the object, tends to be concentrated. But here, the center of gravity is the point where the gravitational force of the Earth can be considered to act. So that's the difference between the two. Center of mass is where the constituent of the object tends to be concentrated, while the center of gravity is the point at which the gravitational force of the act tends to act on the object. So these are some of the differences that we have. Now looking at this object now, the center of gravity The center of gravity can be found experimentally by suspending an object from different points. So you can suspend the object using your retort stand. There's a hole here, you put it here, see whether it will balance off. You put it here until you find it's neither swinging to the right nor to the left. So you can either calculate, so it makes it easier to calculate the center of gravity. And that's why when you are performing an experiment in the lab that involves a pivot, the first thing is to get the center of gravity of your meter rule. So you place the meter rule here, you start shifting to the right, to the left, until you put it on the knife edge or the pivot where it neither swings to the right nor to the left. So you refer to that as your balance point. Thereafter, you can then introduce your masses. So when you put a mass here, you then want to see where the balance point lies on the meter rule. So you continue to adjust. However, the center of mass need not be within the actual object. The center of mass need not. A donut center of mass is in the center of the hole. For a donut, it's in the center of the hole. So that's an example. You find that in the center of the hole. Now, another example we have here is this. The location of the center of mass of the leg is circled. When you stretch your leg this way, this is where the center of mass is located. But when you bend your knee, you can see the center of mass is somewhere here. You can see that it's not within the object. You can see it's outside. That's where the center of mass is. So the location of the center of mass of the leg circle will depend on the position of the leg. So center of mass varies. However, the center of gravity will not vary on the object. So these are some of the differences between center of mass and center of gravity. Now, for high jumpers, those of them that have actually mastered how to position their center of mass, we have a better technique of jumping over the pole. I've developed a technique where their center of mass actually passes under the bar. You can see the way it's moving. They have developed a technique by which their center of mass passes under the bar. So it now makes it for them, if it passes under the bar, that means they become lighter up. So they can then cross over the bar. So this allows them to clear higher bars. So once they have mastered the technique, for their center of mass to be below the bar, it makes it easier. Very, very easy. So here you have the total momentum of a system particle is equal to the product of the total mass and what? Velocity of the center of mass. Velocity of the center of mass. Thus, since we know from Newton's second law that F is equal to ma, that is what we have here. And our A is the same thing as V minus U divided by what? T. So the A you have here is the center of mass. So the sum of all forces acting on a system is equal to the total mass of the system multiplied by what? Acceleration of the center of mass. Can you hear me? Sorry, the network.
Yes, sir. We can hear you now, sir.
You can
Yes,
hear me.
we
Can
can
you
hear
still
you.
see my
Hear you now,
screen?
sir.
Yes, sir,
Can you
can
see
hear
my
you.
screen?
No, we
No,
can't see
sir.
your
sir.
screen.
No, sir.
We can't see your screen, sir.
Can't
How
see it,
about
sir.
now?
We can't hear you.
Yes, sir.
We
Yes,
can
sir.
see it now.
Yes, sir.
We can see it now, sir.
Okay, thank you.
We can't hear you well. Your
So
voice.
now, we can see the difference between center of mass and the center of gravity. Center of gravity lies within the object, and that's the gravitational pull of the Earth on the object. Why the center of mass can vary within an object, could be within, it could be outside. So it's where the mass seems to be concentrated. So now this is particularly useful in the analysis of separations and explosions. The center of mass, which may not correspond to the position of any particle, continues to move according to the net force. Just like we said, the center of mass moves according to the net force, the force that is applied. So you can see the path of the rocket. It moves this way.
That is happening again. We are not hearing
As
anything.
it changes position, you can see as it's coming that the center of mass is this way. As it moves further again, center of mass varies again. It changes. So the center of mass varies from one location to another location. So that is basically what happens with center of mass. So these were some of the things we discussed, collisions, the summary of what we had discussed. And this is where we are. We refer to this as impulse, which is equal to change in momentum. In an elastic collision, the total kinetic energy is also conserved. Momentum and total kinetic energy are conserved in elastic collision. Why in inelastic collision, the kinetic energy is lost? Well, by the time they are coming together, they've lost some energy, either to friction or to sound. So it's lost. So the center of mass of a system is the point at which the external force can be considered to act. That's the center of mass. And that's why you find the rocket. External force tends to act. You can see it's changing as the position also changes. So any question? Any question?
No, sir.
No, sir.
No, sir.
No, sir.
Okay, so thank you.
No,
So
sir.
let me move on to the next PowerPoint slide. I'll stop sharing this.
Sir, we can't hear you.
Oh, I'm coming. I'm trying to share the second slide for the class.
Okay, sir.
Okay. Oh, shit. Okay. This is what we have now. So the next slide discusses about the kinematics of uniform circular motion. I can say basically what we want to discuss is a circular motion. We want to discuss about circular motion, and these are the highlights of what we will be discussing. The kinematics of uniform circular motion, dynamics of uniform circular motion. We discuss about highway curves, the banked and the unbanked, non-uniform circular motion, Newton's law of, no, that will be the next. So we'll stop here under non-uniform circular motion. All these are not for, oh. So now, the kinematics of uniform circular motion. 1, uniform circular motion is a kind of motion that describes the motion of an object. The path takes a circle. And when it takes a circle, we find out that it is always at constant radius, which means here, R here will be equal to R here, which is radius of something like a sector. So if it's at a constant radius, that is why we have the word uniform. Why instantaneous velocity is always tangent to the circle. It's a tangent to the circle. The tangent velocity, like we have our V1 and we have V2, they are tangent to the circle through which the ball moves. Now, under uniform circular motion, we also describe what is referred to as the kinematics. And when you discuss about kinematics, that means kinematics refer to study of the motion of an object as well as the force that is creating the motion. You are studying the motion of an object as well as the force that is creating the motion. That is what is referred to as kinematics. Now, looking at the change in velocity in the limit that the time interval becomes infinitesimally small. So we are looking at the motion is still circular in nature. That's why you saw this curve. You can see this curve now, but you only want to describe a small part of it. Maybe the ball moves from here to here. Just this small path is what you are interested in. That's why we say infinitesimally small. So if you consider that, you can describe its acceleration as what? The square of the speed divided by the radius of the path taken by the object. So the acceleration within that radius is equal to the square of the speed divided by the radius. So from our O levels, we all know that A is equal to what? V squared, that's the speed divided by R. But when you now come here, we all know that the force creating is what? MA. So eventually we have what? MV squared divided by what? Divided by R. We are trying to calculate the force. So please give me a minute. I'll be back.
Hello.
Oh, you're playing Candy Crush. That's my love. You're a fool.
Hello.
You know sense. And then we know the girl.
Do you know about this too? Come and see.
Hunger, word.
Hello.
This hunger.
Joy's come.
Yeah, come on, sister.
Joy's come. How come?
Level.
Yeah, mad.
As powerful. Why are you using 6 passwords? To 4 now. Come and see my WhatsApp. See.
Okay, so
What
a continuation
are you?
of what I was saying.
Let's wait my phone.
No.
You created the video.
So in continuation of what I was describing, when you describe that, this is what you have eventually when you describe an infinitesimal radius, the path through which it has taken. So take note that the acceleration observed within a circular motion is always given as the speed is taken with respect to the radius of the path it is taking. So this acceleration that we have considered here, that we said A is equal to V squared divided by R, we refer to this acceleration as the centripetal what? Acceleration. Centripetal acceleration. That is what we describe it as. And the centripetal acceleration is being created by what is called the centripetal force. And what do they do? What they do is to keep it from not, they keep it in the circular path. The moment the centripetal force is not there, it will go off this circular path. To go off the circular path. If you can remember, while we are young or even now, if you tie a rope to a stone or the cover of a bottle or a bead, and you decide to wear it using your hand, you find out that it moves in a circular path, just like we have here. It moves in a circular path, just like we have here. As it moves in the circular path, what is keeping it in the circular path is the centripetal force, which is this, and is the one creating the centripetal acceleration. But the moment you release your hand off the string, what happens? You see that it goes in the other direction. It refuses to move in the circular path. Maybe it will just fling itself to this side. Because the centripetal force is no more there to give you centripetal acceleration, which keeps it in the circular path. So the moment that force is not there, you see it moving in the other direction. It will refuse to move in the circular path. That is the observation. So I hope it is clear.
Yes, sir.
Okay.
Yes.
Yes, sir.
So
Yes,
still
sir.
explaining this.
Yes, sir. It's clear, sir.
Okay. So the dynamics of uniform circular motion, we can see
Yes,
that
sir.
the force must be inward. So that centripetal force always acts inward towards the center of the circle. It acts inward towards the center of the circle. By thinking about a ball on a string, so the force on the hand exerted by the string and the force on ball exerted by the string. So you can see both of them move up in opposite direction, but concentrated at the center. So once it's there, it will continue to move along that circular path. It moves along the circular path. So these are some of the stuff. So now, when you don't have centripetal force, the opposite you have is what is referred to as the centrifugal. For those in biological sciences, These are some of the things you still make use of in the lab. We refer to those equipment as centrifuge, where you put in your test tubes with some specimen, it jiggles it, and it gives you what you want. Even those in chemistry, you still use it. Even those in the medical sciences, these are some of the facilities that you still make use of. So the centrifugal force will not allow it to move in the circular path. So there's no centrifugal force pointing outwards. What happens is that the natural tendency of the object to move in a straight line must be overcome. So if the centripetal force vanishes, the object flies off target to the circle. If it vanishes, it flies off target to the circle. You can see this now. You can see the direction. It's off that target. The same thing here is off that target. So it moves, flies off target to the circle. So it wouldn't move in the circular path. That is what will be observed. Now let us look at another example where centripetal force plays a lot of role, because we are growing and you also tend to drive in the future, or some of you might have been driving. So it behoves you that when you get to a part of the road that is curved or a bend, you need to exercise caution such that your car does not skid off the road. You need to apply the brakes a bit so that you can keep yourself moving in that path. And that's why you see those performing car racing. During car racing, if the driver does not exercise caution, you find him skidding off the road, because usually it's in a circular manner. So when a car goes around a curve, there must be a net force towards the center, you can see, of the circle, of which the curve is an arc, of which the curve is an arc. So if the road is flat, the force is supplied by friction. If the road is flat, the force is supplied by frictional force. So, but usually around a bend, the force is concentrated at the center of the circle through which it moves. You can see this is a car racing operation. Look at their tires. You can see the friction. Friction of tires on the wrong way through which they move. So if the frictional force is insufficient, the car will tend to move more nearly in a straight line. And that is what is causing it. Instead of making a bend and move this way, it tends to move what? In a straight line this way. And that's why you have this. So these are skid marks that are being shown there. So just explanation of what is observed. So you also have this, the force applied at an angle and gives you a centripetal acceleration. So for non-uniform circular motion, if an object is moving in a circular path, but at varying speed, it must have a tangential component to its acceleration, as well as radial one. So that's why you have tan this way. There's also acceleration. So it must have some component if the speed varies as it's moving along this path. Once the speed varies, you have a varying tangential component. Varying tangential component, and that's what we can see here for both the force and the acceleration. Now let us look at this example. A 150-gram ball at the end of a string is revolving uniformly in an horizontal circle of radius 0.6. So you have this. 0.6 meters. The ball makes 2 revolutions in 1 second. 2 revolutions in 1 second. What is its centripetal acceleration? What is its centripetal acceleration? We all know that acceleration, centripetal acceleration is equal to what? V squared divided by what? R. But however, from this question, the speed is not given. So, and we are to find this, so you cannot have 2 unknowns. We're only giving the radius. Because you cannot have 2 unknowns, that makes it difficult. So we must first of all find the speed at which it is moving. Just like I said here, if the speed is varying along the circle of which it is normal, it is normal. The speed varies, then you have different tangential components of the velocity. So we needed to calculate that. So in order for us to be able to get the speed, and we all know that speed is equal to what? Under mechanics or kinematics, speed is equal to what? Displacement divided by what? Your time. So the displacement here is like the distance. It was here, it was displaced round. So displacement here will be in terms of the distance covered. And in this situation, that means it's going to observe a circumference. So observe what? A circumference. So if it is a circumference, that means the circumference of a circle is equal to what? 2 pi r. So the displacement will be equal to what? 2 pi r divided by what? Divided by the period. Divided by the period. So how do you calculate your period? How do you calculate period?
1 over frequency.
Yes, period from your oscillation and waves is 1 divided by your frequency. So that will be what? 1 divided by what?
Yes.
That's 0.5 seconds. And that's why you have the 0.5 here as your period of oscillation. So you put in the pi, you put in the radius, you are able to get the speed. So once you get the speed, you can then come here inside the speed square divided by the radius. And this is what you have as the acceleration, centripetal acceleration. So I hope that question is clear.
No, sir. No, sir. Sir.
Yes, sir.
Yes, I'm with you.
Sir, does the mass of the ball matter in this? Like, does the mass of the ball matter?
Does the mass? The mass does not matter in this situation. It's only when you are asked to now calculate the centripetal force. That is when the mass matters. Mass times what? Centripetal acceleration. That's when you use it. But you are not asked to calculate the force. So it doesn't matter.
Okay, sir.
So it is not every parameter you have in a question that is useful in solving that particular problem. It's not every parameter. And that is the more reason why you need to get your physics right. And how do you get it right? You need to solve enough problems. Your PNOKK is still useful. Your new school physics, Ayakwa, is still very useful. So don't throw them away. They are very, very useful to you. Those problems you could not sit down to solve while you are in your secondary school, go and pick them up now, sit down and try to solve those problems. And I'm assuring you, once you can solve those problems holistically, there's no way you will not score A in this course. So the more problems you solve, the better you are, and your chances of scoring an A increases. So I hope it is clear. I hope it is clear.
Yes, sir.
Yes, sir.
So
But sir,
we'll
what
continue
about
next. What do you
sir,
want to say?
I wanted to ask, can we just use Adewale Physics Volume 1 to
There is
study?
no problem. If that is available to you, you can use it if the content of what I'm teaching is there. The
Yes,
most
okay,
important
sir.
thing is to understand the physics. At the same time, you are able to solve the problems that are there.
Yes, sir.
So the more problems you solve, the better you are.
Sir, but which textbook will
So that's my
recommend
advice
us?
to you.
Yeah,
Or
send any
any
textbook.
A-level
He said you
physics
can use any
textbook, Gibbs
textbook.
is there. There
New
are so
school.
many. Giancoli is there. There are so many physics textbooks.
Yes.
So solve problems is very key. So God's willing, because it's 5 minutes past 1 now, so that you might have another class. I don't want to encroach into another class. So we'll meet that's on Thursday, God's willing. So we meet on Thursday. We'll continue from where we have stopped today, and we see then.
Thank you, sir.
for
Thank you,
paying
sir.
attention.
Appreciate, sir. Thank you,
Thank
sir.
you.
Thank you, sir.
I'll send the recording to the I'll send the recording to the sub-dean for him to share with you.
Yes.
Thank
Yes,
you,
sir.
sir.
Oh,
And
okay. So it's my pleasure. You're all welcome. Thank you.
Thank you so much.
Thank you
so much, sir. Appreciate you, sir.
The slide.
I don't know. Are they fucking mad? What are we going for? I've not lived it. What's that?
Am I the host? I'm not the host now.
You